Okay, good afternoon. Today I'm going to start by talking in this lecture about two different things. One is multi-class classification. So far we've been looking only at binary classifiers, distinguishing between two classes. We're going to look at how we can extend to multiple classes. And then we're going to take a more theoretical look at where the error comes from. And we're going to look at this decomposition of the error in bias and variance. This is not very important in practice for selecting parameters or models. We generally use cross-validation as you've been using so far. But it's important to understand two different sources of error, and it's relevant for what I'm going to talk in the second lecture, which is ensemble classification and regression too. So we're going to talk about this a bit, about bootstrapping as a resampling technique to evaluate bias and variance, and how this relates to the problem of the error and overfitting and underfitting. But I'll start with multi-class classification. In some cases, classifying more than two classes is trivial because the classifier itself can handle any number of classes. For example, if you have a k-nearest neighbors classifier, since the output is the majority vote of the neighboring points, it doesn't matter if you have 2, 3, or 4 classes. It's the same. You just count which one comes out ahead in all the neighbors. For naive Bayes, it's also similar because you're going to find the class for which the joint distribution between the prior probability of the class and all the data points is maximum. So you just compute this for whatever number of classes that you have, and you take the maximum value. But for other classifiers, things are a bit trickier. So we're going to see, we'll start with this example of this data set, the iris data set, which is a data set of flowers of this genus. And typically this data set has these three classes which correspond to these three different species: Setosa, versicolor, and virginica. And the data set has 4 dimensions, which is the length and width of the sepals and the petals of the flower. And these are the 3 different classes. And we have, if we plot this only as a function of the sepal width and length, so width here, length here, width on the vertical axis, we are looking at a 2-dimensional projection of this data set. So I threw away 2 of the features. But we can see the distribution of the 3 classes. And if we use something like k-nearest neighbors, it's not hard to build a classifier because we simply use the majority vote at each point, and we have a classifier for the 3 classes. The problem is if we use those binary classifiers, for example, binary classifiers that depend on a frontier hyperplane to separate the 2 classes. In this case, if we have more than 2 classes, then we need to do something in order to use these classifiers. And I'm going to show you first 2 solutions that are not very good, but what we learned from those helps us understand how to implement or to extend binary classifiers in order to classify k classes at the same time. So we'll start with one possibility, which is to train. If we have k classes, we're going to train k minus 1 classifiers, and each one is trained to distinguish one class for the rest. So we have this for all classes except the last one, and the last one is the rest of all the others. So to illustrate this, we're going to create, in this case, we have 3 classes. We're going to create 2 classifiers. For each one, we're going to train to distinguish between that particular class and all the other classes. So one class is class 1, the rest is class 0. And we're going to do this for the 2 classifiers. And then we're going to assign each example that we want to classify either to the classifier that outputs 1 for that example, or to the last class if all the classifiers output 0. So this would be, we train one classifier to distinguish Setosa from the rest. We train another classifier to distinguish virginica from the rest, and now we have these 2 classifiers. If the classifier, if our example is classified as 1 for the first classifier and 0 for the second one, then we know it's Setosa. If it's the other way around, it's versicolor. And finally, if both output 0, then it's Virginica, which is the last class. The problem with this is what happens if both of them output 1. So in this region here, we have ambiguity because both classifiers are claiming a point there belongs to their class. So another way of trying to solve this problem is to build k times k minus 1 over 2 classifiers, which is basically all the pairs of 1 versus 1 classifier. So we're going to build one classifier to distinguish Setosa from versicolor, one classifier to distinguish Setosa from Virginica, one versicolor and Virginica. And now we're going to check the outputs and see which is the dominant value, which is the dominant class over all the classifiers for each point. In this case, we still have the same problem of ambiguous areas because there are some areas where there are ties or all classifiers claim that is to be each one claims a different class for that point or whatever, and we cannot solve for all the regions using this way. So basically we have this problem. If you only look at what is classified as this class or that other class, or we only look at the predicted class, we always have these regions where we have ties and we have ambiguity. So one solution for this is to build k classifiers, one for each class, and to train each one to distinguish that class from all the rest. So this is called one versus rest with k classifiers, or one versus all, also called that way. So basically for this example, we build three classifiers. One distinguishing Setosa from all the rest, the other one distinguishing versicolor from all the rest, and the third one Virginica from all the rest. But now we're not going to look only at which class the classifier predicts the point to be in. Because if we did that, we would still have the same problem of having ambiguous regions. What we're going to look at is the maximum value of the decision function. If we are using classifiers that have this hyperplane, remember that the hyperplane is that region where the decision function is 0. But as we move away from the hyperplane, it becomes more positive or more negative. So we can use this continuous value to get, for each point, that classifier which has the strongest prediction. And so if we combine that, we can use the maximum value of the decision function and we remove the ambiguity. So this is a standard way of extending those bisecting, those binary classifiers that have this kind of decision function, to extend them from 2 classes to k classes. We just build k classifiers, train each one to distinguish one class from all the rest, and then use the maximum value of the decision function for each point to classify. The advantage of this is that as long as we have this decision function that we can look at the maximum of, we can avoid these ambiguous regions, because this is now a continuous value, so in general we find one that has a value greater than the rest. The disadvantages, the cons of classification with this method is that first, each classifier is trained on an unbalanced data set. So let's say we have 10 classes, and all our data points are evenly distributed between the 10 classes. So each 10 classes have 10% of the points. In that case, when we're going to classify using this one versus the rest, each classifier will have to distinguish 10% of the points from 90% of the points. So all the classifiers will deal with very unbalanced data, and this may affect their performance. Furthermore, we are comparing decision functions between different classifiers, different hypotheses. And as you remember, the decision function is not only a function of where the hyperplane is, but also that vector that determines the perpendicular to the hyperplane. So depending on the size of the vector, the decision function will vary differently, and we are in fact trying to compare these confidence levels between different hypotheses that may strictly not be comparable. So the overall result may not be as good as it could be. So there are some advantages here, but in general this is a good approach because we don't have those ambiguous regions, and we can train k classifiers, or binary classifiers, in order to classify k classes. There are some classifiers that have some particular modifications that we can do in order to adapt them more specifically to the K-class problem, to multi-class classification. For example, remember that in logistic regression we had that cross-entropy function between the two classes, where we consider the probability of belonging to class 1 and then the probability of belonging to class 0, which was simply 1 minus the probability of belonging to class 1. In fact, we can extend that cross-entropy function to any number of classes. We simply have to multiply all those conditional probabilities of belonging to the class given the vector with the features, and then we optimize that function for all the classes at the same time. So this is one possible extension of logistic regression in order to explicitly adapt it to multi-class classification. In scikit-learn, you have two options when you have more than two classes for the logistic regression classifier. You can specify multi-class with 1 versus rest. This will train the same number of logistic regressions for two classes as the number of classes that you have, and then take the maximum of the decision function. Or alternatively, you can use this multinomial option, which makes this expansion of the cross-entropy function to multiple classes and minimizes everything at the same time. So there may be some problems with the number of dimensions that you have, or the data points, or the number of classes. So there may be some numerical problems, but in theory you could use this natural expansion, explicit expansion of the logistic regression to adapt it to multiple classes exactly in the same way as we use logistic regression for two classes. In the case of the perceptron, we can do this conceptually the same thing as 1 versus the rest classification directly on the neural network. So if you have two classes, you can have just one output neuron, and if it's high value, the output, then it's one class. If it's a low value, it's the other class. If you have more than two classes, you can have as many output neurons as the number of classes that you have, and then you simply take the maximum value. This is the same as implementing in the network the 1 versus rest classification. It's the same idea. You are testing different outputs and you take the maximum one. So in a multi-layer perceptron, all you need is to increase the number of output neurons in order to be the same as the number of classes, and you have a multi-layer perceptron that can do multi-class classification. In general, you can use any classifier for 1 versus rest classification in scikit-learn by using this class here, 1 versus rest classifier. This gives you an object that when you construct that object, you give it a classifier object that this 1 versus rest classifier will then clone that object and train for the different classes. And then when you ask for the predictions, it will run them through all the classifiers, the binary classifiers, and give you the predictions according to the maximum value. So you already have this class to do 1 versus rest classification with any classifier that you want to use. So this is an example of doing for the iris data set projected in these 2 dimensions using this support vector machine classifier with a Gaussian kernel, and then doing the 1 versus rest classification. So what it's being done here is that there are 3 support vector machine classifiers. Each one is being trained on one of the 3 classes, and then the output is the maximum of the decision functions of all the 3. So the class that will be assigned will be the class corresponding to the support vector machine that is outputting the largest decision function. So this was multi-class classification. We're going to change gears now for something completely different, which is we're going to take a more theoretical look at a breakdown of where the error comes from when we are doing classification or regression. So for supervised learning, there are basically these 2 sources of error, bias and variance, and we're going to see how they play together to give us the error that we have on the validation set, on the test set, outside the training set. So let's start with this notion of bias. This is not the same as inductive bias, which I talked about in the first lecture. This is a notion of statistical bias. And statistical bias occurs when the expected value of some measure does not correspond to the true value or to the expected true value of the thing that we're trying to measure. So it's basically a difference in expected value. So let's suppose, to illustrate this, that the model cannot fit the data adequately, and so we have this curve that does not pass close to, say, this point here. If we train the model over different samples of the possible data, so we have our universe of data points is distributed like this, we can sample and draw training sets from that universe of data points, let's say by doing some experiment or something like that. And as we adjust the model multiple times, we get all these different hypotheses, but they, on average, are making predictions for this value that do not span the value. They fall always biased over that value, in this case, overestimating the value. So we can consider the bias for this model to be this average distance between the distance between this average estimate for the values of this point and the true value of the point. So our model is biased because it's always making errors tendentially to the same side. And another concept here is variance, which is the dispersion between the two, between the different predictions that we are making. So let's suppose that we have the other problem, the method is overfitting, and now as we train our model with different data points, with different sets of data points, we get very different hypotheses each time we train. And so now what we get is a very large dispersion of predictions around the true value. And if we measure that dispersion, we can measure the variance of that dispersion, and this gives us the variance value here. So these bias and variance are the measures for the model, and we have in this case the variance for 1 point, which is the quadratic distance between the predictions here over all the different training sets that we use. So we are considering the predictions of different hypotheses generated from the model using different sets of training points, and this is the average prediction over all these hypotheses. So this is the square distance between the two, and we're going to average this for the number of hypotheses that we found, and this will be the variance for a point. So in this case, the variance for this point will be the average of the distances between each prediction and the average of the predictions in all these hypotheses. Now we average that for all the points that we are considering, and we get an estimate of the variance for the model. So the same thing we can do for bias, which is we're going to check for each point the difference between the average of the prediction of the values predicted for that point over all the hypotheses that we're generating. So we are training the model with different data sets, and we're going to see what is the average prediction. So, for example, here, this is the average prediction over a large set of hypotheses. And we compute the difference between that average and the true value of that point. And this squared will be the bias for that point. If we want the bias for the model, we average that for all the points that we are considering. Note that sometimes bias is written as bias squared because we have a square there. But this does not mean that we are squaring the bias again. It's just an indicator of using that square value here. So basically, bias is the square distance between the average prediction when we train the model in many different, generating many different hypotheses using different samples of the data. It's the square difference between that and the true value of the point. And variance is the average squared this difference between each prediction and the average prediction of all those models. So this is something like the variance of a random variable. That's where the name comes from. So basically, we are averaging the distance to the average prediction for all the models. This bar there means that this is the average Y predicted for that point over all the hypotheses we draw from this model, and this is each of the predictions for each of the hypotheses.
So that M is the model.
The hypothesis we generate from the model, yes.
And the variance is basically for every model we measure
the squared difference. Yes.
The average, and then we do the difference.
So we have. So imagine we have the average for all these lines here in the center, and now for each line we have a difference between the predicted one and the average for all the lines. And now we average the squared values of all these differences. And this gives us a measure of how spread out they are. And for bias, what we do is we average the prediction for all the lines, and then we measure the squared difference to the true value. So this tells us how much to the over or under our model is aiming. Okay? So these are two measures that we can consider: the dispersion around the average prediction, that's the variance, and how our model is aiming, if it's aiming crookedly, if it's aiming outside the target, which is bias. So note that both bias and variance are measures that correspond to the model. They do not correspond to any single hypothesis, because we have to average over many different hypotheses to get an estimate of bias and variance. So now, how can we measure bias and variance, and what good is this for? The idea is that if we have a quadratic error function, as is typical in regression, we can consider that the expected error that we're going to find can be decomposed into these three terms. This is the expected square difference between the average predictions that we make, so this expected y is the average of y, and the average value, true value of each point. Now here, in general, we've been considering that each point has one true value, but we also are considering here this noise. So noise means that when you are measuring the true value of a point, there may be some experimental error or some fluctuations in nature itself that is not a function of your model. That's something that is going wrong. So generally we're going to consider that this is zero, because this is not something that we can control in machine learning, the quality of our data. It is relevant in some cases to consider it, but for machine learning itself, for this more theoretical approach, we will assume that our data has no noise in that. So this would be the actual true value, and this is the bias that we are measuring. Here is the dispersion of the predictions relative to the average of the predictions. So the average of the difference between each prediction and the average of the prediction squared. And then the noise we're going to ignore, because we cannot do anything about that. So basically, we can decompose the quadratic error into bias and variance, into how much our model is meeting the target on average, and how much our model is dispersing the predictions around the average. So now, if we can compute these two, we can get an estimate of the error. The thing is that to compute bias and variance, we need to average these measures over a large number of hypotheses trained for that particular model. So this means that we need a large number of training sets. Each different training set will give us a different hypothesis. But we generally only have one training set. We're not going to repeat all the experiments or download more data or something like that to do this. So we're going to use a resampling method. In particular, we're going to use bootstrapping. This is a bootstrapping. Bootstrapping is a resampling method to obtain data sets that are distributed in the same way as our original data set, but are not the same set as our original data set. And to do this, we take, if we have n points in our data set, we sample our own data set, so our own sample, with reposition, and we take randomly n points from there. Since we are sampling with reposition, this means that we can sample repeatedly the same point. So on average, we will tend to leave out 1/3 of the points. So 1/3 of the points we never, in each sample of that, 1/3 of the points we don't copy into our replica, and 2/3 of the points come with some repetition, some of them repeated. So each time we do this, we generate a different replica with a different set of points with some repetitions from our original sample. If our original sample is representative of the universe of possible points, then each replica will behave similarly to that universe of possible points with a similar distribution of values. So this is basically the idea. From our training set, we sample with replacement at random, and we generate m replicas all with the same number of points. But they are all different because they have different, the points that we chose are not always the same, and some come repeated, some are left out, so we have different sets of points. And now we're going to use those replicas to train our model for each of them, and then to compute bias and variance over those different hypotheses. Note that we are looking at an error estimate. So in fact, we don't want to measure bias and variance on the training points, but only on those points that are outside.
But that means that the replicas will have 2/3 of the points of the original...
Yes. On average, each replica will have 2/3 of the original points with some repetition. So for each replica, there is about 1/3 of the points that is left out, and we can use those for testing. So basically, we use the ones that are inside each replica to train the hypothesis, and we use the ones that are outside to measure what we need to measure for all those points. So this is an example of code to generate the replicas. It's a bit, it's not very optimized, but the idea is just to show you in detail what we're doing. So we have this training set, which is a three-dimensional matrix which has as many layers as the number of replicas that we want, and for each layer we have a matrix with the same size of our initial data matrix. So we're going to generate one layer for each replica. And now we're going for each of those replicas, we're going to create a random array of integers that goes from 0 to the number of points that we want, and the number of random integers that we want is also the number of points that we have. So we are generating an array with random rolls of the dice in order to choose each point for our training set. But note that this array can have repetition. So there are points that there are values there that will appear several times. So now we're going to copy from our original data set all the lines indicated by that array into this layer of our replicas matrix. So into this matrix of the replicas. This means that this replica set will have some repetition and some points are left out, and because this was all chosen at random with repetition. And now we're going to find which were the points that were selected. We're going to call this unique function which tells us the different values that are in that array. Remember that some of them are repeated. We're going to throw away the repetition. And now we're going to create a mask of true values and set to false everything that is inside the training set. So basically, we have a set of Boolean values indicating those points that were not chosen for the training set. And these will be the indices we now append to our test set. So our test set will be lists of integer indices indicating which points are outside for each replica. And this is how we create the replicas for bootstrapping. So for each replica, we have a matrix that is identical to the one that we use, started from, only with some repetition, and we have the indices of all the points that were left outside. Now we can use that to decompose this polynomial regression into bias and variance. So this is just, the idea here is just to show you the details of all the steps. You're not going to do this in practice because in practice we will use cross-validation to optimize parameters. But if you understand what we're doing here, then it's easier to understand some consequences of this. So we're going to create all these replicas, all the predictions for our points, And then for each replica, we're going to train one polynomial with the specified degree on all the data points in our replica. And then we're going to predict, to compute the predictions for all the points that this polynomial is giving us. And now here we're going to compute the bias and variance. So we have all these, we're going to count each time we find a point in the test set, because we don't know for all the replicas how many times each point appears on the test set. So this is this vector here that counts for all the points. And then we're going to look at the predictions for the test set, and we're going to sum those predictions, and we're going to sum the squares of the predictions. This helps us compute the variance, because the variance can also be computed as the difference between the average of the squares and the square of the average. So this is just another way, a simpler way of computing the variance. So we're going to do that for each point. In each point we have the sum of the squares divided by the number of times the point appears. This is the average of the squares, divided by the square of, minus the square of the average. So this gives us an array with the variance for each point. So how did this appear? Because we are looking at the predictions of the polynomials computed with different replicas. So we are computing as many polynomial regressions as replicas that we have. And then we're going to use the statistics from that. And this gives us the bias, which is just the mean, the average prediction minus the actual value for the point squared. So this way we can look at the polynomial regression with different degrees of the polynomial and decompose the total error into bias and variance. If we assume that the error on the data is 0, then the sum of the bias and variance will be the error for each model with each degree. So this is what we get here. This is the total error in red, and here we have bias in green and variance in blue. So we can see how this relates to underfitting and overfitting. When we are underfitting, we have a very low variance because the model is not adjusting too much, so there is no big spread in the prediction. But we have a very high bias. We can have a high bias because the model cannot fit the data, and so for each point tends to predict always to one side, either over the point or under the point. As we increase the degree of the polynomial, bias will start to decrease and the overall error decreases. So here we are at that sweet spot where we minimize the test error. But then eventually we start getting a model that too easily adapts to the point, so it adjusts to all the noise that appears here. And variance starts to increase greatly. And this increases the overall error. So we can see here the relation between bias and variance and underfitting and overfitting. So this would be for the lowest total error. This is a bit strange. I think there is a problem with the projector or the cable. Okay. So this would be the polynomial for the lowest total error, which is here at degree 3. So we can see now that there are these two components for the error. When we are underfitting, our model tends to overshoot or undershoot the real point, and does so in a biased way. When we are overfitting, bias tends to be very small, but since our model can generate hypotheses that vary a lot, then we can have a large error because of the variance. So this was for quadratic error, which is typical in regression. In classification, we generally don't have a quadratic error. We have this sort of error, this sort of loss function. So it's basically 0 or 1 if we are 0 if we hit the correct class, or 1 if we fail the class. So if we are basically trying to minimize the number of errors. When we have this 0, 1 loss function, then things are a bit different, because now it's not so much about the average prediction, but the main prediction, which is that one which most hypotheses make, and this would be the mode of the predictions over all the hypotheses. So, assuming there is no noise for the point, we consider the bias to be either 0 or 1, depending on whether the majority of the predictions hits the correct class for that point. In this case, bias is 0, because most of the time our model is predicting the point correctly, or if there is most of the predictions are predicting the point incorrectly. In that case, bias is 1. And variance would be simply the average of this loss function. So the average of, or the expected error rate for our model. So now, to compute the total error, we must consider two different cases, because if for that point, for each point, our model is biased, that is, our model tends to predict the point incorrectly, then having a large variance is good, because it means that it is predicting it incorrectly, but it's predicting it correctly more times than if the variance was low. But this is the other way around if the bias is 0. So if our model is predicting that point correctly, the more bias it has, the greater the number of times it will predict it incorrectly. Even though the most of the time it predicts it correctly, it's different predicting it correctly 51% of the time or 99% of the time. So if it predicts it correctly 99% of the times, it will have a lower variance, even though the bias is still at 0. So this would be our error decomposition in this case, ignoring noise, will be the average bias for our point, and then we will add the contribution. So if bias is 0, this means that the model classifies the point correctly most of the time. But it's different if it classifies the point correctly 51% of the time or 99% of the time. So if it classifies it correctly 51% of the time, we have a larger variance, because there's a larger difference between the different classifications that we're having. If we have a very low variance, this means that it's classifying the point correctly most of the time or nearly all the time. So if the bias is 0, then having more variance is actually increasing the error, because it means it's missing the point more times. Even though most of the time it gets it right, it's missing more times. But it happens the other way around if bias is 1. So making a correct classification 49% of the time, or incorrect 51% of the time, this means that it has a bias of 1. But that is not as bad as making a correct classification only 1% of the time, in which case variance would be very low, because it's always predicting the same thing, but it's always wrong. So in that case, the error is greater. So basically, if bias is 0, we want low variance, because high variance means we are making more mistakes. If bias is 1, yes, but the more variance tends to occur when we're overfitting. But for this particular case, for the decomposition, we want to consider these two cases. For the point where bias is 0, a lower variance is good, higher variance is bad. But for those points where bias is 1, it's the other way around. Okay? So let's see an example for optimizing a radial basis function kernel support vector machine. We're going to optimize the radius of the kernel, and we're going to do something very similar. So we're going to start with our replicas. We're going to train our support vector classifier for the different replicas. So if we have 500 replicas, we have to do 500 times the training, but we're going to compute all the class predictions for all those trainings. And now we're going to do the same thing. We're going to look at the test points, so we have to count how many times they appear, and we also have to sum their predictions. I'm summing the predictions because we have class 0 and class 1, so just by adding the predictions, I know how many times class 1 was predicted for each point, and class 0 will be the remainder. So now the main prediction, we simply round the sum of the predictions divided by the total. So if it's more than 1/2 of the time, it's predicted class 1. If it's less than 1/2, then most of the predictions are class 0. And now we're going to compute the bias for each of the points, and now we're going to do this different variance for the unbiased points, which are those where the bias is equal to 1, and the biased points, which are those where the bias is equal to, where bias is equal to 0 for the unbiased points, and bias equal to 1 for the biased points. So we are splitting these into two, and now the total error, we have the bias, and we have this total variance, which is the variance for the unbiased points, because this one contributes positively to the error, minus the variance for the biased points, because this one will decrease the error. And now we can do this for different values of gamma. This is actually the logarithm of gamma because of the way gamma affects the error rate, and we see the same thing here. So we have a large bias initially, it decreases, and then we have variance eventually increasing on this side. So this is the same kind of plot, or underfitting, overfitting, but now we are decomposing into bias and variance. So this is an example for the best gamma here, which has a value of 1. So basically, reducing bias increases variance, and this is what gives us that trade-off between underfitting and overfitting, or the bias-variance trade-off that we usually, is the way it's usually called. So note that bias-variance decomposition is useful for understanding where these errors come from. But this is not something that you'll generally do in practice. It's a lot easier to do cross-validation to estimate these errors and optimize parameters than to do all the replicas and do bias-variance decomposition. However, it's important to understand where the errors come from for what we're going to talk about in the next lecture, which is combining families of classifiers in order to improve either reduce bias or reduce variance without affecting the other. So one way of trying to cheat this bias-variance trade-off. So in summary, we saw how to do multi-class classification. That part was a bit easy and obvious, but we also saw this distinction here between bias and variance. It's important that you understand what these are. Basically, bias is a measure of how tendentially our model makes mistakes. So on average, it's making a similar mistake every time. Variance is a measure of how spread out the predictions are. And depending on the conditions, if we are underfitting or overfitting, we may be increasing one of these errors by decreasing the other. So in general, we have to find those best spots where the right balance between the two is found. So here are some sections where you can read, and optionally you have some papers if you want to look a bit deeper at deriving these equations, but this optional part is not required for the course. So I recommend that you read those sections in the textbook, and the papers only if you're really. So do you have any questions now?